In this video, we'll take a look at structural isomers, also known as constitutional isomers. And the first thing that we need to know is what is the definition of an isomer, and an isomer in general must have the same molecular formula but a different arrangement of atoms. So what this implies is that it's a relationship between two molecules or more molecules, so you have to have at least two that you're comparing together, and if they're going to have an isomeric relationship, they must have the same molecular formula, meaning that all the atoms, the elements that make up that molecule, are exactly the same. So you have the same number of carbons, same number of hydrogens, same number of heteroatoms, etc. It must be exactly the same for the two molecules to be isomers of each other. Now, structural isomers in specific are a special type of isomers in which they have a different connectivity. So what this term means, this connectivity term, means that the bonds between the atoms in the molecule are different. So like for instance, you could have a chlorine or some other halogen or some other heteroatom for that matter is bound at a different carbon in your molecule. Let's say you have a chlorine bound at carbon 1 and a chlorine bound at carbon 2 in two different molecules. Those would be isomers of one another. And we'll look at an example like that right here. So here's the example that I was just referring to. So first of all, they must have the same molecular formula. So there's three main ways to count that and to determine that. I'll go through each one of those. But for now, I'm just going to say they have the same molecular formula, and we know they're structural isomers because the chlorine is bound at a different carbon. So here it's bound at 1, or this position here, if you count left to right, it would be 3. But remember, if you're going to do IUPAC naming, it would be at 1, chlorine is at 1, and the chlorine is at 2 here. So that's what I mean by different connectivity. The bonds are literally placed in different spots, which is why we call them structural isomers, because the structure is different. Now, there's three main ways to go about determining the molecular formula and then therefore getting to the structural isomer feature. So the first way that I've dubbed is just the brute force method, and this is simply just counting each atom in on every single point of the structure. So here we have skeletal structures, so all of the hydrogens are implied, so you need to count each one and then sum up the total, and in order for them to be isomers, they would have to have the same total, the same molecular formula that you find when you count them all up in that way. The second way is basically the same as brute force. It's just it uses degrees of unsaturation to determine the number of hydrogens without actually counting all of them. So it's a little bit of a shortcut compared to the brute force way. Again, I'll get into the specifics of that, but you can count the degrees of unsaturation and determine the number of hydrogens rather quickly when you get comfortable with it. And then lastly, IUPAC naming. This is most specific to actually determining the structural isomer themselves. Structural isomers are going to have different IUPAC names. So if you just IUPAC name them using the systematic name and nomenclature, you will get a different name if they are structural isomers. If you get the same name, then they're just the same molecule represented in a different way. All right, now I'm going to go into detail of each of those three types of methods that I defined for determining structural isomers. So first is brute force. So what this method involves is you just have to count all of the atoms in your molecule to determine the molecular formula. So to do that, looking at our same examples that we had here before, you would first count the carbons. Remember, in the skeletal structure, all of the endpoints of a carbon, of a structure have a carbon there, and all the hydrogens are implied at those endpoints to give you the octet. So here, you just start by counting the endpoints. There's 3 carbons. That's where we get C3 here from the 3 endpoints. Then you count your hydrogens. So at carbon 1, there's only 1 bond shown. That means there has to be 3 carbon-hydrogen bonds that are not drawn but are implied there. So we have 3 hydrogens. Here we only have 1 because there's 2 bonds to the separate carbons, 1 and 3, and then there's a bond to the chlorine going up. So that's 3 bonds. So to have the octet of 4, with 4 bonds giving the 8 electrons, you would need 1 more carbon-hydrogen bond at position 2, which gives us a total of 3 plus 1, which is 4. And then we look at carbon 3. There's only 1 bond shown, so there has to be 3 more. So 3 plus 1 plus 3 is 7. And then we count anything that's left, which is just this heteroatom of the chlorine, and that is present there, and that gives us the whole molecular formula. Do the same thing over here. If we look at carbon 3, only one bond is shown, so there's 3 hydrogens there, that's 3. Then we add 2 here, because there's 2 bonds shown, that's 5. And then 2 here, because there's 2 bonds shown, that is 5 plus 2, which is 7, gives us the 7 hydrogens. And then, of course, we have the chlorine. So all this tells us is that they can be isomers, because they have the same molecular formula. Because remember, identical molecules will also have the same molecular formula. So all we've determined at this point is they can be isomers of each other. Now we have to determine if they are isomers and what type. So next, it's about determining the position and the connectivity of the different atoms in the molecule. So when we go about looking at that, we see that our chlorine here is bound at position 2, as labeled up here at the top. Carbon 2 has the chlorine. Here it's at carbon 1 or carbon 3, depending on how you count, but it's a different position. So from there, without doing any naming or anything, we can say that these are structural isomers because they are isomers with different connectivity, and this is what we call structural or constitutional isomers. Those are the same terms, just used interchangeably. All right, the next method for structural isomer determination is counting the degrees of unsaturation. And really what you need to know, so I refer to these as DOU, degrees of unsaturation, and what you need to know is that a point of unsaturation occurs with rings and pi bonds. And essentially, it takes 2 hydrogens to have a point of unsaturation. That you need to remove those 2 hydrogens from a fully saturated compound to give that point of saturation. So this will make more sense as we go through specific examples, but what this really implies is that you can determine a given structure's degree of unsaturation by simply counting the number of pi bonds and rings. But you have to remember that a triple bond has 2 pi bond features, right? It's a sigma and 2 pi bonds, giving the total of the 3 bonds for the triple bond. So you would have to count those as 2 pi bonds, 2 degrees of unsaturation. But otherwise, it's simply just adding up how many rings, how many pi bonds that you have. Okay, so next, this is the point of this is the usefulness of this, I should say, is that it can check the molecular formula rather quickly, because molecules with the same degrees of unsaturation, the same number of carbons, and the same number of heteroatoms will have the same molecular formula. So simply, you can just count your endpoints to get the number of carbons, count your heteroatoms that are present, like chlorine in our previous example, and then count the degrees of unsaturation. If those 3 features are the same, the molecular formula has to be the same, and this will save you a little bit of time because you don't have to count all of the hydrogens individually. For most molecules, this isn't going to save you a lot of time because many molecules don't have several degrees of unsaturation. But let's say you're going to look at like a steroid molecule or something that has 4 rings and some possible other points of unsaturation like pi bonds and things like this. It's much easier to do it this way, so you don't have to count 30 hydrogens or something like that. So you kind of want to use all of these methods interchangeably at what's most useful for the problem at hand. So anyway, using this method now on our example is we just look for our degrees of unsaturation. And as I mentioned, it's the pi bonds and the rings that count of degrees of unsaturation. So here we only have sigma bonds, single bonds, no rings. So we have 0 pi bonds, 0 rings. So the degrees of unsaturation are the same. Then using the brute force method before, we've already counted the carbons are the same. There's 3 carbons and 1 chlorine in both of them. So therefore, the degrees of unsaturation are the same, number of carbons are the same, number of heteroatoms are the same. Therefore, it's the same molecular formula without having to count all of the hydrogens. All right, and the last method is determining the IUPAC name, the systematic nomenclature name for each of the structures. This is definitely the hardest method here to determine the structural isomers, but you can kind of use it to check if the other methods, like if you're unconfident in the answer for the other methods, you can use that to check. So the main point of this method of determining structural isomers is that structural or constitutional isomers are going to have a different IUPAC name. Systematic nomenclature will be different for those structural isomers. So this arises directly from the different connectivity. Remember, we've defined structural isomers, constitutional isomers, as having different bonds at different positions in the structure, in the molecular structure. So the name will reflect that. It will indicate the position in which the the bond is different. So that's why we can use the systematic nomenclature to check this as well, to determine if this is a structural isomer. So again, looking at our chlorine example, or chlorine example, we again go through this IUPAC nomenclature system. So we count the longest chain. There's only 3 carbons here, so the longest chain is propane. And for the molecule here on the left, it doesn't matter if you go left to right or right to left, because the only thing that's present is the chlorine. So you want the lowest numbering system for that chlorine, which is 2 in either directions. It cannot be 1 or 3 for that matter. So the lowest numbering system is as drawn, which gives us 2-chloropropane as the name. Then we go to the molecule on the right. This one, it does matter now, because if we numbered it left to right, it would put the chlorine substituent at carbon number 3, which is higher than 1, which we can put it at 1 if we just start the numbering system right to left, which is what we must do, and therefore it's 1-chloropropane, and these are different systematic names, and therefore they're structural isomers because they have a different systematic name. All right, for the remainder of the video, we are going to take a look at a few example problems. And the question is, determine if the following molecules are structural isomers of each other. So to do this, we have our 3 methods of the brute force, degrees of unsaturation, and IUPAC naming. So let's just start with brute force. So the first thing we have to do is, in order for them to be structural isomers, they have to be isomers in general. Which, remember, isomers in general have to have the same molecular formula. So we first need to confirm that the molecular formula is the same, otherwise they cannot be isomers at all, and they're just different molecules entirely. So we can count with the brute force method, so we just count our endpoints for the number of carbons. So we have 6 carbons here. Then the hard part is counting the hydrogens, which you can do with degrees of unsaturation or brute force counting the hydrogens, so we'll do both. So first, let's look at carbon 1. That has 3 bonds shown, so there's 1 hydrogen there. Carbon 2 has 2 bonds shown, so there's 2 there, so 2 plus 1 is 3. 3 is the same as 2, so that also has 2, that's 5. 4 is the same as 3 and 2, so 5 plus 2 is 7. 5 is the same as 2, 3, and 4, so that's 7 plus 2 is 9. And 6 is also the same as 5, 4, 3, and 2, so that's 11 total hydrogens, and then the 1 chlorine. All right, so C6H11Cl, or you can count the degrees of unsaturation. Here we have 1 ring, no pi bond, so the degrees of unsaturation is only 1 because it's in the form of the ring. Okay, let's move to the next one over here. So again, let's count the carbons. So we have 1, 2, 3, 4, 5, 6. Carbons are good. Next, we can look at the hydrogens explicitly. So this carbon rather, has 2 hydrogens because 2 bonds are shown. So 2, this one only has 1, so that's 3. Again, there's 3 bonds shown, so you only have 1 additional hydrogen there. So that's 3, plus 2 here is 5, plus 2 here is 7, plus 2 here is 9, plus 2 here is 11. So they do have the same number of hydrogens, and then of course the 1 chlorine. Now again, you could have just checked the degrees of unsaturation. There's 1 ring, so that's the same. So we brute force check the molecular formula, it's the same. We check the degrees of saturation, that's the same. The number of carbons in heteroisomer are also the same. So either way you do this, you're going to get the exact same molecular formula. So these can be isomers, right? That's all we know at this point, is they can be isomers. We now have to determine, are they structural isomers or some other type? Well, here we have a 5-membered ring versus a 6-membered ring. So those are completely different types of bonds. The chlorine is off of the ring here. It's off of just a single methylene carbon here, CH2, off of the ring. So the connectivity is completely different. So these are structural isomers. Now you could have checked the IUPAC naming system as well. So for this, the longest chain is the 6-membered ring. So let me redraw it over here just to give some space. So the longest chain is the 6-membered ring. All right, so that is cyclohexane. and then you have the chlorine at the 1 position, so that's 1-chlorocyclohexane. You probably will see this as just chlorocyclohexane because the 1 can kind of be implied, since if you can't put it at any other position besides 1 if there's only the single substituent in the ring, as you would start your numbering system at the substituent every time, regardless of where it was shown in the structure. Then if you look at the 6-membered ring, so here you have to consider the longest chain as the 5-membered ring, so that's going to be cyclopentane. And then the substituent here is a complex name because there's a substituent within the substituent, because this is just a 1-carbon branch, call it 1' to be different than the carbon number 1 that is in our ring. But this is a methyl group with a chlorine on it, so this entire substituent is a chloromethyl. And since it's complex naming, you put it in parentheses. Now, this is where the IUPAC convention is good to check the structural isomers, but if you aren't comfortable in some of these naming conventions, you can definitively know the answer using brute force and the degrees of unsaturation. IUPAC nomenclature is simply to kind of confirm what you've determined from the other ones. At least in this context, you need to use IUPAC naming just to know what the molecules are and different from each other so you can talk about them. So anyway, here is the next question, B. So again, the question is, are these structural isomers? So we need to first determine, can they be isomers? So is the molecular formula the same? So let's start by counting the carbons. Here we have 4 in this first molecule and 4 in the second molecule. Now, we can always brute force and count the total number of hydrogens individually, but I think the way I would do this is just count the degrees of unsaturation to kind of expedite the process. So we know that there's 4 carbons in both, right? So 4C, or I could put C sub 4 if it was in the molecular formula. I'm saying 4C here because we're not going to count the hydrogens. Now, let's count the heteroatoms. Well, there's 1 chlorine in both. So the carbons and heteroatoms are the same. Now let's count the degrees of unsaturation. In this first one, we have 1 pi bond, so it's 1. So 1 pi bond. And then in the second one, we have none. 0 degrees of unsaturation. Because there's only single bonds, only sigma bonds. So right away, this tells us that the molecular formula is not the same. And again, I think this is the better way to do it because you don't have to count the hydrogens individually. So from the degrees of unsaturation argument, we say that this molecular formula is not the same, so these cannot be isomers, like a generic isomer. So they cannot be specific isomers like structural isomers. All right, here we have our next set of questions. So again, the question is the same: determine if these are structural isomers. So the very first thing we need to do in all of these questions is determine if the molecular formula is the same. If the molecular formula is the same, then they could be isomers. So again, let's just count the carbons and the degrees of unsaturation to kind of expedite the counting process. So here we have 6 carbons in the ring, and then 3 carbons exocyclic, or outside of the ring. So 9 total carbons. Do the same thing over here. We count the carbons in the ring, that's 6, and then there's 3 exocyclic. So 9 carbons in both. Now count any heteroatoms. There are none here. This is simply a hydrocarbon. There's only hydrogen and carbons. So the heteroatoms are the same because there's 0. Now let's count the degrees of unsaturation. Here we have a ring and a pi bond, so that's 2, 1 ring and 1 pi bond. Here we also have 2, 1 ring and 1 pi bond. Right, so total of 2 degrees of unsaturation in both. The number of carbons is the same, the number of heteroatoms is the same, so these could be isomers because they have the same molecular formula. That is the conclusion. They have the same molecular formula. Now we have to consider In this context, we're talking about structural isomers. So we need to consider, is the connectivity the same or different? So let me redraw both structures so we can look at this a little bit more easily. Right, so let's start the numbering system at the same point relative to one another. So what I mean is, let's start numbering at the pi bond. All right, so let's number here 1, 2, the pi bond this way, where we name the carbon number 1 of the pi bond is bound to that propyl group, the 3-membered substituent. So let's do that the same over here. Okay, so what we see is in both of these molecules, what we've just determined is that the propyl group can be labeled at position number 1 in both of them. I'm circling it now in blue, right? So that is the same at the same labeled carbon. Right? Then we move to carbon 2. That is the same as well because it's a part of the pi bond. Right? So far there's no difference at all. Then we can continue and finish the naming system, the numbering system, I should say. And we see that they're the same at each carbon. Right? Carbon 2 is a part of the pi bond. On the other side, not with a substituent, that's the same in both. Then we move to carbon 3, that's just a CH2 of the ring. CH2 of the ring, that's the same. 4 is the same. 5 is also the same. 6 is the same. Then we get back to 1. Nothing has changed. So the only difference between these two is a simple rotation. So these are the exact same. These are identical molecules. Therefore, not isomers. At least not structural isomers. Because the connectivity is exactly the same. Right? There's no difference in the binding. It's just the orientation, the perspective that we're looking at it is different, which does not have any implication on structural isomerism. All right, and moving on to our last question of this video. So again, we're asked, are these structural isomers? So we need to count the molecular formula, determine the molecular formula, is that the same? So again, I recommend just counting the carbons and the degrees of unsaturation. So our carbons, we have 6 in this first molecule. Count the heteroatoms, there's 1 oxygen. And then move to our second molecule here, count the carbons again. There's 6. Count the heteroatoms, there is 1, so that's the same so far. Now let's count the degrees of unsaturation. We have 2 pi bonds in carbon-carbon pi bonds, and then a third pi bond in a carbon-oxygen pi bond, so 3 total pi bonds. So 3 degrees of unsaturation. And then we go to the other structure. There's 2 carbon-carbon pi bonds and 1 carbon-oxygen pi bond, exactly the same. So we have 3 total pi bonds. So again, the conclusion from this step so far is that the molecular formulas are the same, and therefore they can be isomers. So now we have to determine, is the connectivity the same or different? So again, I'll redraw these so we can look at this again more closely. Okay, so again, just like we did in the last question, let's count the carbons in a way that's the same to each other. So here we have to either go left to right or right to left to keep them consistent, and there's no seeming difference. So let's go left to right to left. Again, this is not IUPAC naming, this is just to compare the same carbons to each other. Since there's no ring or symmetry, we just need to compare kind of 1 to 1, basically. So carbon 1 to 1 here is exactly the same. This is just a alkene group at the exact same carbons, that's the same. We move now to carbon 3, and this is different now. 3 has another carbon-carbon double bond in this first structure. 3 has a carbon-oxygen carbonyl double bond that is different here. And then we move on to carbon 4. 4 now has a new carbon-carbon double bond. Again, we don't have that in 5 here. We have a carbonyl. So what this is telling me is the connectivity is different. Here we have another way of putting it, we have conjugated pi bonds that are carbon-carbon pi bonds. And in this feature here. Let's say carbons 1 to 4. Right, here we have no conjugation between carbon-carbon bonds. It is conjugated between the carbonyl, which is the same over here as well. But the main point, that's another way of looking at it, the main point is the connectivity is different, right? The bonds are different. So due to the different connectivity, these are structural isomers. All right, that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or question or anything like that, feel free to leave it down in the comment section below, and I'll get to it as soon as possible. But with that, I hope you have a great day, and I'll see you in the next video.